Hello, I'm Erdem from Stanford. Today I'm going to talk about how we actively learn nonlinear reward functions. This is a joint work with Nicolas, Huynh, Mykel, Kochenderfer, and Dorsa, Sadigh. Let's say we have a user who wants a robot to perform a task. The user has an internal reward function that she wants the robot to optimize. However, the robot doesn't know this reward function. For example, in this case, the user wants the robot to play a variant of minigolf where each target you see below has different scores. The user knows the scores, but the robot doesn't. As it's very difficult to teleoperate fetch due to its high degrees of freedom, we take a preference-based learning approach, where the robot shows a trajectory to the user and then another one. The user then tells the robot which trajectory she prefers. Prior work in the literature, including some of our works, assumed a reward function linear in some trajectory features. Here, the features are task-specific. For example, for this minigolf task, the ball's distance to each of the targets might be the features. The goal is then to just learn the weights. The problem that's sometimes overlooked is these features are very hard to design. If you look at these previous works, you will often see feature descriptions like this. There's an exponential function, and then there's this constant that no one knows where it comes from. Sometimes these features get even uglier. For example, we have another exponential here, but with the distance squares now, and there are again some magic constants. Older works have proposed feature generation algorithms in the learning from demonstration setting. And in recent years, deep learning techniques alleviated this feature design problem, but they are not applicable in preference-based learning because data collection is very expensive. What makes the problem harder is, if the features are not well designed, then the system can totally fail. For example, in this minigolf task, it should be sufficient to have the shot speed and shot angle as the features to successfully hit the ball into one of the targets. But with linear rewards, the optimal shot is going to end up in either of these 4 points, because the robot will try to either maximize or minimize the speed and the angle. Of course, it would be possible to keep the linear function if we defined a new feature for each and every target, representing the distance between the ball and a target. But this approach is not scalable. Instead, we want to model the reward as a nonlinear function of features, such that the optimal behavior can now correspond to any point in this contour. If we can learn such a nonlinear reward function, then the feature design will not be that difficult because the reward function will handle it. The first thing that comes to mind is of course to model the reward as a neural network. But remember, the only feedback we get is pairwise comparisons. Training a neural network with such data without overfitting would take too many samples. Answering hundreds or thousands of questions, the user would be really unhappy. Our idea is to use Gaussian processes because they can be efficiently used with a small number of data samples. So the Gaussian processes improve data efficiency over neural networks, but we want to improve our data efficiency as much as possible, because each query gives at most 1 bit of information. Therefore, on top of using Gaussian processes, we should actively generate the queries to maximize the information gain. Let's now look at how our framework works. The robot will keep a Gaussian process. Using this model, it will generate the pair of trajectories that will give the highest expected information gain. Of course, I'm skipping a lot of mathematical details here. It will show the trajectories to the user, who will then respond to the query. We will store this response in a database. Here we are using the probit model for human responses. Depending on how close the rewards are to each other, this model produces probabilities that are close or different. Using this model, the dataset will give us a likelihood function, which we can use for fitting the GP. While it doesn't fall into the class of GPs, we can use Laplace approximation to cast the posterior as a GP. The process will then repeat using this posterior. Now I want to show you some videos from our user studies. Let's start with looking at some queries made to the user. Here I'm showing you an information optimal query when we model the reward as a linear function of features. As you can see, the robot hits the ball to the boundaries, because it believes one of the extremes must be optimal. However, we can significantly improve expressiveness if we model the reward using a Gaussian process. As you can see in these video clips, the robot can now hit the ball to the different regions. So the GP modeled reward enables the robot to explore a broader range of trajectories. Now let's go back to our diagram and look at the learned policies. Again, the linear reward model is unable to generate a good shot, but the GP model efficiently learns the reward function and achieves hitting the desired target. After learning the reward functions, we asked the users randomly generated queries and checked how good the learned reward functions can predict their responses. As you can see, GP modeled reward achieves a higher prediction accuracy, so it's more expressive. We also showed the optimal trajectories with respect to the learned rewards to the users and asked them to evaluate how good the shot is. The users preferred GP reward over the linear reward. To summarize, we have developed an active preference-based GP regression technique in our work, and we used it for learning reward functions in robotics tasks. If you want to utilize this GP regression in your projects, our code is open source. Thank you.